Have you ever just felt completely swamped by information? Like trying to drink from a fire hose. It feels almost impossible sometimes to cut through all the noise and figure out what's really going on underneath. Well, that's exactly why we're here on the deep dive. Our whole mission is to take these really abstract, sometimes complex ideas and ground them in ways that are surprisingly clear, maybe even fascinating, so you walk away feeling, truly informed. Today, we are embarking on a deep dive based on this really extraordinary note I read. It connects dots you probably never even thought were connected. We're going to explore these fundamental links between energy, living systems, even the health of our communities. Our mission really is to uncover how concepts that seem worlds apart, like, say, uncertainty, natural selection, social dynamics, how they're all surprisingly linked through some very, very fundamental principles. Okay, so let's start with a concept that sounds simple, but it's actually incredibly profound: uncertainty. When you think about it, uncertainty is just everywhere, isn't it? Predicting the weather, the stock market.
Oh, absolutely. It really is. And here's a core idea that, well, it really changed how any scientist look at the world. Uncertainty isn't just some vague feeling. It's actually measurable, quantifiable,
Yeah.
fundamentally linked to information itself. Think of it like this. The more choices or possibilities there are in any system, the more uncertain it is. And the more bits of information you need to completely specify its state. This goes way back, actually, to Ludwig Boltzmann in the 19th century. And now, it's a cornerstone of modern physics and information theory.
Right, and we deal with this kind of uncertainty all the time, don't we? Even just estimating risk day to day. Like, imagine someone says there's a 1 in a million chance of winning something. That sounds incredibly rare. We know that intuitively. But to really get a feel for it, it's like flipping a coin 20 times in a row and getting heads every single time. Seriously, try to picture that in your head. It gives you this visceral feeling for just how lucky or maybe unlucky a 1 in a million chance actually is. It's just a huge number of outcomes.
It's a really powerful illustration, yeah, because it shows how incredibly quickly possibilities can multiply. And this way of understanding uncertainty, it's remarkably useful, not just for risk, like you said, but also for information processing or even understanding heat in physics. Thermodynamics. In fact, many modern physics textbooks, they now introduce temperature not just as, how hot something feels, but as a direct measure of the uncertainty within a system. It really highlights how universal this concept is. Now, that example, the coin flip, that's where every choice is equally likely, heads or tails. But what happens when the choices aren't equal? When some outcomes are more probable than others? Okay, so this is where the math gets a little bit more sophisticated. But it lets us factor in how surprising each outcome is based on its probability. Think of it this way. If an outcome is super unlikely, you'd be very, very surprised if it actually happened, right? So this refined measure of uncertainty, it accounts for that. It gives us a much more precise picture when probabilities aren't all the same.
That's a great way to put it. Surprise factor.
Okay, so if uncertainty is about the number of choices, what happens when we start looking at the relationship between those choices? This is where I think it gets really interesting. It leads us to something called net surprisal.
Exactly. Net surprisal. It's essentially a measure of how different the probabilities you actually observe in a system are from what you expected them to be. It's a way of quantifying correlated information. So for instance, if you're rolling a die, you expect each side to be equally likely, right? 1 in 6. But then maybe you start seeing the number 6 come up way more often than chance would suggest. That deviation, that unexpected pattern, that surprise, that's what net surprisal captures. It highlights these hidden correlations. And here's what's truly fascinating, connecting it back to physics. In thermal physics, this net surprisal isn't just some abstract information number. It directly measures something called thermodynamic availability.
Thermodynamic availability.
Okay.
Okay, what's that exact? It's the ordered energy, the usable energy in a system that's actually available to do work. Think of like a perfectly organized toolbox versus just a random pile of tools and parts. The toolbox has high available work. You can build something easily. The messy pile, not so much. This measure, net surprisal, it's also inversely proportional to the ambient temperature. Or you could say it's directly proportional to coldness, which is reciprocal temperature. And here's a real mind bender. This measure even applies to situations that seem totally paradoxical, like negative absolute temperatures.
Negative absolute temperature, how is that even possible? Isn't absolute zero the coldest possible?
Yeah.
Well, yes, in the conventional sense. But these negative temperature systems, like you find in some lasers, they're actually counterintuitively hotter than any positive temperature system. Why? Because they're in such an extreme state of disequilibrium, they possess a massive amount of usable energy ready to be released. Their net surprisal is huge. So this net surprisal, this measure of correlation and usable energy, it has incredibly wide-ranging applications, way beyond just thermal physics. Think statistical analysis, quantum computing, and crucially for our discussion today, understanding how complexity emerges, especially life here on Earth, which is fundamentally driven by the available energy pouring in from the sun.
That's incredible to think these abstract math concepts, quantifying information, surprise, usable energy, they might hold the keys to understanding life itself. But how exactly do we get from there, from these abstract ideas like broken symmetries, which you see when, say, water freezes into a structured snowflake? How does that relate to the emergence of something as complex as a living system?
Okay, yeah, let's connect that to the bigger picture. The emergence of complexity very often starts with what physicists call broken symmetries. Imagine something totally uniform, amorphous, like a liquid drop or maybe a piece of glass before it crystallizes.
Mm.
It looks pretty much the same from every direction, right? Isotropic. But when that glass reorganizes into a quartz crystal or water freezes into that intricate snowflake, that initial uniform symmetry is broken. The crystal or the snowflake now has a definite structure, specific axes, facets. In this sense, these more organized forms actually represent an increase in complexity because there's now more that's macroscopically knowable about them compared to their original, less structured states.
Okay, so breaking symmetry leads to more knowable structure, more complexity. How does that apply to life?
Well, for living systems, the source material argues that the most fundamental broken symmetry is what it calls an in-out symmetry. This is simply the formation of a boundary. Think of a cell membrane. Suddenly, what's inside is distinct from what's outside. This boundary allows for a unique internal environment, totally separate from the surroundings. And once you have that boundary, that distinction, a process of natural selection can really start acting on those enclosed systems. It's a critical step. It means a whole new level of complexity has been established, a new phase of matter, you could almost say.
Wow. Okay, so this boundary, this inside-outside distinction, that's the crucial leap. But how does just having a boundary lead to all the complexity we associate with life?
Right, the boundary is necessary but not sufficient. You also need a continuous flow of that available work we talked about, that usable energy. Given that energy flow, the system inside the boundary can start to develop these incredibly intricate correlations, ways of relating its internal parts and ways of relating to the outside world. So inward-looking and outward-looking correlations. Think of these correlations as ordered information, specific relationships, patterns. These are what allow the system to maintain itself, to preserve its structure, and even, eventually, to replicate over time. But here's a key point. Unlike energy itself, which just transforms but is conserved overall, these correlations, this order, is fragile. It can be lost very easily. It can degrade into randomness, thermalize into disorder, which means living systems constantly need a fresh input of ordered energy just to maintain these correlations, just to stay organized.
So life is constantly fighting disorder by using energy to maintain these correlations, these patterns.
Exactly. And the source material describes life on Earth as developing through layered complexity. It suggests there are stacked levels, and each level has its own in-out boundary, its own characteristic symmetry break. We can think of these boundaries pretty broadly. You start with the cell membrane, obviously, then maybe the surface of a tissue in a larger organism, then the skin of a whole multicellular organism, like us. But then it goes further into more abstract boundaries, like the edge of a specific gene pool, or even the boundary around an idea pool.
An idea pool. Okay, that's interesting. And this layering leads to what the source calls correlation buffering activity layers. Layers that manage information flow across these boundaries.
Precisely. They actively look both inward and outward from each boundary, managing these crucial correlations. And for us as multicelled organisms, the source really focuses on 6 primary layers, described as independent physical levels. Let's list them out. First, you have skin looking in. That relates to our own body's fitness, our wellness, maintaining our physical self.
Okay, skin in, fitness, got it.
Then, skin looking out. This is about our immediate social sphere, our friends, our mentors, the direct connections we make.
Skin out. Friends, mentors. Makes sense.
Next level up, gene pool looking in.
Yep.
That's our immediate family, our relatives, our direct lineage.
Gene pool in, family.
Right.
Then gene pool looking out. This broadens to our wider community, our involvement in politics, perhaps, connecting with our larger genetic or tribal group, you could say.
Gene pool out. Community politics. Okay.
Then we get to the idea pools. Idea pool looking in. This represents our traditions, our culture, the shared knowledge and beliefs passed down within our specific group.
Idea pool in. Culture traditions.
Fascinating.
And finally, idea pool looking out. This is about our profession, our engagement with science, with broader systems of knowledge, how we interact with the global exchange of ideas.
Idea pool out. Profession science. Wow, that's quite a framework. 6 layers mapping our existence from the body right out to global ideas. So, okay, stepping back, what does this all mean for how we understand life, society, maybe even ourselves? This idea of layered complexity, especially these higher level pools, seems like it could have some pretty profound implications.
Oh, indeed. I think it really does. One of the most truly fascinating implications is this concept of gene pool life forms and idea pool life forms. The idea is that these higher level entities can actually undergo natural selection above the level of individual organisms.
With selection acting on groups or even ideas themselves.
Kind of, yeah. For example, think about multicelled animal communities. If offspring are treated differently based on their genetic lineage, maybe some groups protect their related young more fiercely than others, then that difference in behavior can lead to selection pressure on the gene pool itself. The gene pool life form associated with a more protective behavior might thrive. Similarly, in human communities, if one culture, one set of ideas, an idea pool life form is treated differently, maybe suppressed or promoted over another, then those ideas, that culture, experiences a form of natural selection.
Huh. So biologists don't necessarily call these life forms yet.
Well, maybe not explicitly in everyday lab talk, not usually. But the source points out that the analytical framework's definitely moving in that direction. You see echoes of it in really influential ideas like Richard Dawkins's selfish gene concept, the gene as the unit of selection. Or look at David Sloan Wilson's work on group selection, how selection can act on entire groups, not just individuals. And there's even a classic 2010 paper by Martin Nowak and his colleagues on eusocial communities, think ant colonies, beehives. They suggest these communities can be modeled essentially as pure gene pool life forms, where the individual ants or bees are like the moving parts, the cells of this larger entity.
Okay, so the analysis is heading that way, but let's bring it back to the listener. Why should you care about this idea of gene pool or idea pool life forms? What's the so what? How does it connect to your experience right now?
Well, consider this perspective shift it offers. When we report on casualties from, say, a natural disaster or a conflict, we typically count the individual body count, right? But this framework suggests maybe we should also be trying to inventory the damage done to the gene pool life forms and the idea pool life forms that those individuals belong to, communities, cultures, ways of life. And this raises a really important, maybe slightly uncomfortable question. What if these higher level life forms, these gene pools and idea pools, aren't always benign? What if they can be, well, quite aggressive and sometimes act in ways that don't actually serve the best interests of the individual organisms, the people they're made of?
Can you give an example?
The source gives a stark one from the animal world, the male grizzly bear that sometimes kills a prospective mate's existing cubs. From the individual cub's perspective, or their mother's, it's obviously terrible. But from the perspective of the gene pool life form associated with that male bear, it makes a kind of brutal sense clearing the way for his own genes. He's acting in a way symbiotically with his gene pool. And the source then draws a parallel, suggesting this resonates with certain situations today where some individuals seem to have an unexpectedly strong symbiotic relationship with a particular idea pool life form, a specific ideology or culture that, maybe from an outside viewpoint, doesn't seem to serve the broader interests of other human cultures or even all individuals within that culture. It offers a lens on certain social dynamics, maybe even culture wars.
That's a challenging perspective, but it leads us to a potentially really practical application of these ideas, doesn't it? How can we use this framework to, say, monitor the health of our own communities?
Exactly. The source material suggests we can use something called activity layer multiplicity as a kind of order parameter, an indicator for community health. This basically means looking at how well those 6 layers we talked about are functioning and accessible for individuals within the community. Let's recap them quickly. Fitness wellness, skin in; friends mentors, skin out; relatives family, gene pool in; community politics, gene pool out; traditions culture, idea pool in; and profession science, idea pool out.
Okay, so tracking the health across all 6 layers.
Right. And what's fascinating is the source notes that individuals are actually unlikely to excel or even be deeply engaged in all 6 layers simultaneously. The estimate given is a geometric mean of about 4.25 out of 6.
Only 4 and a bit, so most people aren't fully active everywhere.
Apparently not. And this is precisely why institutions, cultural institutions, political ones, educational ones, professional groups, are so absolutely crucial. They act as the scaffolding that helps us collectively keep all these different layers intact and healthy for the whole community, even if individuals specialize. In fact, this individual limitation, this specialization, might even be an advantage. It could foster a really wide variety of adaptive perspectives and ideas across the population. Good for innovation, good for resilience.
That makes sense. So, how does understanding these layers and our limitations connect directly to challenges that we might be facing right now?
Well, the immediate focus highlighted in the source material is, and I'm quoting loosely here, the urgent need for rebalancing communications, specifically to ensure we're covering issues across all these layers, beyond just the often divisive sort of tribal issues that seem to be favored by what the source terms rogue idea pools, those that seem to underpin these electronically mediated culture wars. So this framework offers a new lens, a different way to maybe view and potentially address some of these really complex, very challenging social dynamics. It suggests some of our biggest societal conflicts might be understood, at least partly, as clashes between these higher-level idea pool life forms.
Wow. Okay, what a journey we've been on. We started with something seemingly simple, uncertainty, measured in bits. Then we saw how it connects to usable energy, thermodynamic availability, even this wild idea of negative temperatures actually being hotter in a useful sense. Then linking that to broken symmetries, birthing complexity, and life itself emerging as this cascade of layered complexities, creating these gene pool and idea pool life forms that the source describes undergoing their own kind of natural selection. It really is a profound potential shift in how we might view not just biology, but our own societies, our cultures, everything.
Absolutely, it's a big conceptual leap. And the source material does highlight the potential here for this framework to prompt maybe a significant shift in scientific understanding. It even suggests the need for perhaps a formal paper aimed at biologists, extending the way physics recognizes new phases through broken symmetry, to apply that thinking to this layered complexity we see everywhere in living systems. So this really invites you, the listener, to consider the implications. If we start to truly recognize these higher level life forms, these idea pools and gene pools, how might that change your understanding of society, of cultural conflicts, maybe even of ourselves and our own motivations? How do you see these idea pool life forms playing out in your own experience? And what might recognizing them mean for how we communicate, how we try to foster healthier communities, and just navigate this incredibly complex world around us? Lots to think about.